Hello friends. So today we are going to solve some questions from modern physics, and these questions are from the year 2004. 4 questions, and we have 2005 6 questions, 2006 2 questions, and 2007 also 2 questions. So in totality we are going to solve 14 questions. So the first question, it was asked in the year 2004, and it states that wavelengths belonging to Balmer series lying in the range of 450 nanometer to 750 nanometer were used to eject photoelectrons from the metal surface whose work function is 2 electron volt. Find in electron volt the maximum kinetic energy of the emitted photoelectrons. Take the product of Hc as 1242 electron volt nanometer. So here we are given that wavelength is belong to the Balmer series, and for Balmer series we know the transition is going to take place for the value of n, that is equal to 2. So we start from there only. So you can say Balmer series transition to value of n is equal to 2, and work function is given to us along with the range of wavelength is also given. The range of wavelength is 450 to 750 nanometer. So first of all we are going to find out the highest energy or shortest wavelength with respect to the Balmer region, and specifically with respect to the given wavelength. Okay, so we can say highest energy, or we have shortest wavelength. Shortest wavelength in a Balmer series for the given range. For the given range, and for the given range the transition we already know the lowest is our n is equal to 2, so we are going to find out the highest one. So the transition is from n is equal to 4 to n is equal to 2. Therefore, corresponding to these two value of n, we are going to find out the energy associated with each level. So we can say our E of 4 will be equal to minus 13.6 divided by our 4 square, and this will be giving us minus 0.85 electron volt. Similarly, we are going to find our E of 2, which will be coming as minus 13.6 divided by 2 square, which will be coming as minus 3.4 electron volt. And from here we are going to find out the difference between these two energy levels. Let us suppose that difference is our delta E. So we can say delta E will be equal to E of 4 minus E of 2, which gives us minus 0.85 minus of minus 3.4, and this gives us 2.55 electron volt, and this will be nothing but our, we can say, energy of photon. So we can also write it as energy of photon will be equal to the difference in energy, and this will be coming as 2.55 electron volt. So based on this, we can easily find out the maximum kinetic energy using photoelectric equation. So you can say using photoelectric equation, and which gives us that our maximum kinetic energy K max is equal to energy associated with the photon and minus the work function phi, and all the values are known to us. So we can say our K max will be equal to energy of photon is our 2.55 and the work function is 2. So this comes as 0.55 electron volt, and this is the value of the maximum kinetic energy emitted by the photoelectron. Next question. It was also asked in the year 2004, and it states that a rock is 1.5 into 10 to the power 9 year old. The rock contains 238 uranium, which disintegrate to form 206 lead. Assume that there was no 206 lead in the rock initially, and it is only stable product formed by the decay. Calculate the ratio of the number of nuclei of uranium-238 to that of lead-206 in the rock. Half-life of uranium-238 is 4.5 into 10 to the power 9 year. So in this case, it says that the age of the rock is given. So we can say that T is given to us. So we have age of rock, which is suppose equal to T, given as 1.5 into 10 to the power 9 years, and half-life of uranium is given. So we are given as T half of uranium, and that is given as 4.5 into 10 to the power 9 years. And it is said that initially there is no lead, only the uranium is present, and this lead is a stable product. And we need to find out the ratio of the number of nuclei of uranium to that of the lead. So we are going to use decay law, and decay law gives us that our value of our anytime t is equal to n naught e raised to power minus lambda t. And here we can, because initially only uranium is present, we can say that our N naught is initial number of uranium nuclei, initial number of uranium, and our this N of T is our remaining uranium after time T. Remaining uranium after time T. And we already know the value of lambda, that is a standard formula which gives us natural log of 2 divided by T half. And let us assume that the number of uranium left is suppose Nu. Let us assume that number of uranium, that is uranium 238 left, is suppose Nu, and let us assume, for the sake, let us say this is our N. Okay, we can just later on formulate the formula accordingly. So therefore, number of lead 206 formed. Let us call this as NPB, which will be equal to initial minus that of our uranium 238. So we need to find out the ratio. So from here we can just directly write that the ratio of uranium to that of lead will be equal to our N naught minus N. And we are supposed to find out ratio of N naught upon N. Okay, so we need to find out N naught upon, okay, so we can say that ratio N upon N naught will be equal to our, that is our e raised power minus lambda T, which will be equal to lambda, we already know, is our natural log of 2 divided by T half, and this can be written as e raised power minus, and we have natural log of 2 divided by T half and multiply by T. And this can be further solved at, if we take minus 1, this will be our T, so it will be coming as 2 raised power minus T divided by T half. So we first of all, let's find out T upon T half. So we get T upon T half will be equal to 1.5 into 10 to the power 9. This comes as 4.5 into 10 to the power 9, giving us 1 by 3. Therefore, from here we get our N upon N naught will be equal to 2 raised power minus 1 by 3. And this can be approximately as 0.79. So we can further write, therefore the ratio of Nu upon Nb, let me write it here also, this can be written as 1 upon, this will be our N naught upon N and minus 1. And or we can just reverse it, much more convenient. So we can say that our ratio of our lead upon uranium, it can be written as N naught minus N divided by N, giving us N naught upon N minus 1. So we just found out the ratio N naught upon N, and one second, N upon one second, is it correct? N is equal to N naught upon N, and this comes as N naught upon N minus 1, and this is correct, N upon N naught. So we get this as let me sort it out. So we have Nu upon one second. Yeah. So we can just write it as Np upon N naught will be equal to 1 minus 0.79, and this will be coming as 0.21. There is some problem somewhere. One second. Got it. So we get this as Nu upon N naught. My mistake. Forgot something. And this comes as approximately at 0.79. Therefore, we can write then Npb upon N naught will be equal to 1 minus 0.79, which comes as 0.21. Now it's correct. And finally, we are supposed to find out our Nu upon Npb, and this gives us 0.79 and divided by 0.21, approximately 3.76. Sorry, I messed it up. Okay, next question. It was also asked in the year 2004, and it states that after 280 days, the activity of radioactive sample is 6000 dps. The activity reduces to 3000 dps after another 140 days. the initial activity of the sample in DPS is. So we are given the activity after 280 days is given as 6000 DPS. So we can say that after 280 days activity, let us call this activity as A1, it is our 6000 DPS, and after it says that after another 140 days, this we have keep in mind, so we can write it as after 280 plus 140 days, then it comes with respect to the initial activity. So we can say this as activity is our A2, which is given as 3000 DPS, and initial activity, let us suppose, is our A0. Initial activity, let us suppose that is A0, which is basically at t is equal to 0. So here we can easily use exponential decay law, and exponential decay law, which gives us that activity at any time t will be equal to initial activity A0 e raised to power minus lambda multiplied by t. So we have two values of t, so accordingly we can just modify this particular equation. So you can say at t is equal to 280, we have activity is 6000, so we can write this 6000 is equal to A0 e raised to power minus lambda, and t is our 280, and we have at t is equal to 420, we are given at 3000, that is our A0 e raised to power minus lambda, and this comes as 420. So from here we are going to find out value of lambda. So we simply divide these two equations. We can write this as our 3000 divided by 6000 is equal to A0 is going to cancel with A0, and we are left with e raised to power minus lambda 280 e raised to power minus lambda 420, and this gives us 1 upon 2 is equal to e raised to power, this will be coming as minus lambda, and we have 280 minus 280, or we can say if we take minus it will be coming as 280 and minus of 420, and this will be, let us take, this will be your minus 280 and so this will be our minus, giving us minus of 420, and this gives us 1 by 2 e raised to power and minus of lambda 140, This is minus and this will be plus. Minus this will be equal to 0. Yeah, this looks good. And 1 second. E raised power minus lambda 280, and this will be 1 second. So this will be coming as minus lambda 140. Yeah, this is good now. So we can just write that our minus lambda 140 will be equal to natural log of 1 by 2, which can be written as minus natural log of 2, giving us lambda times 140 is equal to natural log of 2. So we have lambda is equal to natural log of 2 divided by 140. And we can just use this value in any of the equation, and from there we can write that our 6000 is equal to our E naught e raised power minus natural log of 2 divided by 140 and multiply by this is 280. This gives us that of A naught is equal to minus, this goes by 0, 0 and this goes by 2. So minus 2 natural log of 2. And we can write this as our A naught e raised power 2 square, and we have here natural log of 1 by 4. and this will be equal to our 6000 is equal to our A naught, and we have this as 1 by 4. This also gives us that A naught is equal to 24,000. This looks good now, 24,000. So we have option number D is correct. And this can be also solved by using the half-life, because if we see that the sample decreases from the 6000 to the half of our 3000. So we can just use the concept of half-life also in order to solve it. And this is more traditional way to find out the answer. Answer will be same in both the cases. Next question. It states that the energy of photon is equal to kinetic energy of the proton. The energy of proton is E. Let lambda be the de-Broglie wavelength of the proton and lambda 2 be the wavelength of the photon. The ratio of lambda 1 upon lambda 2 is proportional to. So we are given that energy of the photon is equal to kinetic energy of the proton, and energy of photon is given to us as E. So we can say that energy of photon is given to us as E. So from here we can say that our kinetic energy of proton let us call this as Kp, that will be also equal to our E, because it is mentioned in the question. And wavelength associated with proton is lambda 1 and lambda 2 is photon. Okay, and we are given that wavelength associated with photon is our lambda 2 and wavelength associated with the proton is our lambda 1. We have to find out their ratio or with respect to E, because the solution is with respect to E. So let us start with the photon. So we can say that photon wavelength is given to us as lambda 2. From here we can write that energy associated with the photon, that is our E, will be equal to hc upon lambda 2. From here we can write our lambda 2 is equal to hc upon E, and proton de-Broglie wavelength that is given to us as lambda 1, which will be equal to h upon p, and the kinetic energy associated with the proton, kinetic energy of proton is our half m v square, and that is also given to us as E. So we can just equate it with E. So from here we can find out our velocity. So we can say that velocity is equal to twice E upon m and its square root. So from here we can find out the momentum, that is our P. P will be equal to mass into velocity. This comes as mass twice E upon m, which gives us square root of 2m multiplied by E. Therefore, we can write that our lambda 1 will be equal to h upon square root of 2m times E. Now we can just find out the ratio of our lambda 1 upon lambda 2. We can say our ratio lambda 1 upon lambda 2. Lambda 1 is our h upon 2me square root, and lambda 2 is equal to hc upon E. Here h and h cancels out. We are only interested in our E. So we can write this will be equal to our E upon C multiplied by 1 upon 2m square root and multiplied by square root of E. So we can write this as we can say in terms of proportionality. So we have here E as well as square root of E. So this comes as E upon square root of E. Therefore, the ratio lambda 1 upon lambda 2 is proportional to square root of E, or we can say E raised to power 1 by 2, I think. Yeah, option number B is correct. Proportional to E raised to power 1 by 2. Option B is correct. Next question. It was asked in the year 2005, and it states that X-rays are incident on the target metal atom having 30 neutrons. The ratio of atomic radii of the target atom and to that of the helium is 14 raised to power 1 by 3. So based on this, we have two questions, A and B. In A, it states that find the mass number of target atom. In B, find the frequency of K alpha line emitted by this metal. Value of Rydberg constant, that is R, is 1.1 into 10 to the power 7 per meter, and speed of light is 3 into 10 to the power 8 meter per second. And here we are given that the number of target atom is having 30 neutrons. So we are given that the number of neutrons in target atom is our 30, and we are also given that the ratio of the atomic radii. So we can say radii of the target to a radii of our helium is equal to 1 upon I think here is to be minus, so this comes as 1 upon 14 whole raised to power 1 by 3. And we are also given the Rydberg constant as well as the velocity of light. So first of all, we are supposed to find out the mass number, and for that we are going to use the radius formula, or we can say nuclear radius formula, which gives us that from nuclear radius formula we can say that value of R is equal to over R naught a raised to power 1 by 3, and we can just reformulate according to our target as well as radius of helium. So we can write this as our radius of target upon radius of helium will be equal to our A of target and four whole raised power 1 by 3, and this ratio is given to us. So we can say this ratio will be equal to our 1 upon 14 whole raised power 1 by 3, and from here we can say that our A of the target divided by 4 is equal to 1 upon 14. This gives us that A of the target is equal to 4 upon 14, approximately equal to 0.2857. One second. Sorry, this is positive, my mistake. And let me write here minus, and this also minus, and here I'll just reverse it. And this will be equal to 14. So we get that our A of target will be equal to 14 to 4, which comes as 56. Therefore, we can say that mass number of target atom is equal to 56. Okay, so please remember this is not minus, but this is positive. Okay, and in the part B, we are supposed to find the frequency of this. Okay, and so from here we can just find out our frequency. Part B, it says that frequency of K alpha line, and we know that the K alpha line is basically your X-ray line due to the transition from N2 is equal to N1. We can say the K alpha X-ray line is due to transition from N is equal to 2 to N is equal to 1. So we can just use the formula directly, and we can say that our frequency F will be equal to our RC multiplied by our Z effective square, and we have this as 1 square minus 1 upon 2 square, which comes as RC Z square effective, and this will be our 3 by 4. And we know that for K alpha line, the inner electron is screened by 1 electron. So from here we can find out our Z effective. So we can say for our K alpha line, the inner electron is screened by 1 electron. So therefore, our Z effective will be equal to our Z minus 1, which gives us that our, okay, we already know the mass number, we can find out the atomic number, that will be our 26. Okay, so let me find out atomic number will be equal to, that is our Z is equal to A minus N. N is the number of neutrons, that is 30. So we get from here that our Z will be equal to A is our 56 minus value of N is 30. This gives us 26. So we get this as a 26 minus 1 is equal to 25. Therefore, we can write that our frequency will be equal to, Rydberg constant we know is our 1.1 into 10 to the power 7. Speed of light is our 3 into 10 to the power 8, 25, and we just found it to the 3 by 4. So therefore, we get our frequency will be equal to 1.54 into 10 to the power 18 hertz. I think this was, yes, frequency is 1.54. Next question. And one second, I think I forgot to mention one thing here, that because of this atomic number, we can also say that this is our iron, that is our Fe. Okay, that's why we say this is our effective, Z effective required. Next question, it was asked in the year 2005, and it states that a photon collides with a stationary hydrogen atom in ground state inelastically. Energy of colliding photon is 10.2 electron volt. After a time interval of order of microsecond, another photon collides with the same hydrogen inelastically with an energy of 15 electron volt. What will be observed by the detector? So we are going to find out what will be the energy associated with both the photons, or we can say individual energy. It says that for two photons energy is either 10.2 or 1.4, or it says that energy associated with one photon is 10.2 and that of other is 1.4. And this is with respect to electron as well as the photon combination is also made in part C and D. So for the first photon, it is said that the energy is 10 point, colliding photon is 10.2. So we are given first photon, and its energy is about 10.2 electron volt. And in the case of first photon, we have to remember that hydrogen is in ground state. So we can say hydrogen is in ground state. And because of this first photon, the energy required to excite the hydrogen from N1 to N2 is about 10.2 electron volt. We can say that energy required to excite hydrogen from N equal to 1 to N equal to 2 is also our 10.2 electron volt. So it means because of the first photon, the electron from N to 1 to N to 2, and the atom is now basically in first excited state. Therefore, we can say the first photon excites the electron from N equal to 1 to N is equal to 2, and the atom is now in the first excited state. First excited state. Now it states that we have to wait for microsecond. You can say that wait for microsecond and we have to remember that this excited hydrogen is basically unstable, and for this fraction of second, that is microsecond, the lifespan of the excited state for the hydrogen is typically 10 to the power minus 8 second. So if we wait for this microsecond, so let me write it here, that our excited hydrogen atom is unstable, and the typical lifetime of excited state is 10 to the power minus 8 seconds, and typical lifetime of an excited state is approximately 10 to the power 8 minus 8 seconds. So it means if we wait for few microseconds, the atom, that hydrogen atom, de-excites back to the ground state. Okay. So from here we can say that the atom de-excites back to the ground state. Ground state emitting 10 raised to power 2 electron volt photon. Ground state from n is equal to 2 to n is equal to 1, emitting 10 raised to power 2 electron volt photon. And this happens before the second photon is arrives. This happens before second photon arrives. And the second photon is of 15 electron volt. 15 electron volt. And here we have to remember that the hydrogen atom is in ground state. Is in ground state. And second photon, the level of energy is 15 electron volt, which is much more than the ionization energy of the hydrogen for the ground state. And we can say that our 15 electron volt is much more than the ionization energy of hydrogen atom from ground state. Ground state. And that values typically we know is our 13.6 electron volt. Therefore, there is a, we can say, difference in energy that will be resulting in the excess of energy. So we can say that second photon ionizes the hydrogen atom, ionizes the hydrogen atom, and we have excess energy. And that excess energy is over 15 minus 13.6, which comes as 1.4 electron volt. And this excess energy goes into the kinetic energy of the ejected electron. This 1.4 electron volt goes into kinetic energy of ejected electron. So therefore, we can say that the first photon, the atom is excited from n to 2, and then it de-excites, which basically emit 10.2 electron volt. So we can say that option number C is our correct option, because one photon energy is 10.2 and electron is having energy of 1.4 electron volt. So option C is correct. C is correct. Next question. It was also asked in the year 2005, and it states that K alpha wavelength emitted by an atom of atomic number Z is equal to 11 is lambda. Find the atomic number of an atom that emits K alpha radiation with the wavelength 4 lambda. So here we are going to use Moseley's law, which relates our wavelength according to the, you can say, effective nuclear charge. So you can say our Moseley's law we can write that wavelength lambda is proportional to 1 upon Z minus 1 whole square, and this is an approximate especially for our K alpha line. And we are given that when value of Z is 11, wavelength is lambda. You can say for Z is equal to 11, we are having a wavelength that is given as lambda, and we have to find out a new atomic number. Let us suppose that is Z prime, and the wavelength is given as 4 lambda, and that is equivalent to, let us suppose, lambda prime. So we can say that for new atomic number, which is our Z prime, wavelength is, let us suppose, is our lambda prime. So this lambda prime will be equal to 4 times lambda. 4 times lambda. Therefore, we can divide, let us put this as equation 1, according to our Z is equal to 11 and Z is equal to, atomic number is 11 and atomic number Z prime. So we can say from equation 1, we can write that our lambda is proportional to Z minus 1 whole square, or our Z prime proportional to Z prime minus 1 whole square. We can easily find out the ratio. Therefore, we can say our lambda prime to lambda is equal to, we have this as Z minus 1 whole square and Z prime minus 1 whole square. And Z prime is our 4 times lambda. So this gives us 4 times lambda divided by lambda is equal to, Z is our 11. So this comes 11 minus 1 whole square, Z prime minus 1 whole square. And lambda goes with lambda. So this we are left with our 10 upon Z minus 1 whole square. So this gives us that our 100 upon Z prime minus 1 whole square is equal to 4. Therefore, Z prime minus 1 whole square is equal to 25, giving us Z prime minus 1 is equal to 25. Therefore, Z prime is equal to, not 25 but 5. Z prime is equal to 6. So option A is correct. Next question. It was also asked in the year 2005, and it states that if a star can convert all helium nuclei completely into oxygen nuclei, the energy released per oxygen nuclei is mass of the helium nucleus is 4.02 AMU and mass of oxygen nucleus is 15.994 AMU. And it says that all of the helium is converted into our oxygen. So we have to understand that our oxygen, that is our 16, is having 8 protons and 8 neutrons. Okay. And each helium nucleus is having 2 protons and 2 neutrons. Okay. So we can say that our oxygen, it is consisting of 8 protons and 8 neutrons, and our helium, it consists of 2 protons and 2 neutrons, and it says that all of the helium is completed into oxygen. So it means if we want to form one oxygen, we can say that to make one oxygen, we have to find out the number of helium, and we can just write it that we are having 8 protons plus 8 neutrons, that is our oxygen requirement, and of helium we are having 2 protons plus 2 neutrons. Or basically we can say we are going to require 4 helium nuclei. Now let's find out our total mass of 4 helium nuclei, and you can say that total mass of 4 helium nuclei will be equal to 4 times, and we have this as 4.0026, and this comes as 16.0104 AMU, and for one oxygen mass is already given to us. So we are given that mass of one oxygen molecule that is given to us as 15.994 AMU. And from here we can use the mass defect, because the total mass which the 4 helium is going to provide is of 16 point something, whereas the actual mass of one molecule of oxygen is 15 point something. So obviously some mass be lost in the form of energy, which we can say as a mass defect. So we can say that our mass defect that is our delta M will be equal to 16.0104 minus 15.994, and this mass defect gives us that the delta M will be equal to 0.010, and this is in AMU, and we can convert this in mega electron volt multiplied by 931 mega electron volt, and this comes as approximately equal to 10.241 mega electron volt. So option number C is correct. C is correct. Next question. It was also asked in the year 2005, and it states that the potential energy of a particle varies by the equation, which states that when the x is between 0 and 1, energy is our E naught, and when it is greater than 0, energy is our 0 potential energy. And it states that between this, when x is between 0 and 1, the de-Broglie wavelength is lambda 1, and for x greater than 2, the de-Broglie wavelength is lambda 2. The total energy of the particle is 2 times E naught. Find lambda 1 upon lambda 2. And we can write the given equation into more elaborated way, and we can say that our energy U of x will be equal to E naught, and this is for our x greater than 0 but less than 1. And for this particular range, the wavelength is given to us as lambda 1. Similarly, we can write that our U of x will be equal to 0 when our x is greater than 1, and for this particular range, our wavelength is given to us as lambda 2. And we are given that the total energy of particle, that is 2 E naught. So obviously total energy is the summation of the kinetic energy as well as the potential energy. And let's find out, because the equation is given in terms of the potential energy only, and the total energy is given as E naught. So from here we can find out the total kinetic energy. And we can also write that total energy that is our E is equal to kinetic energy plus potential energy. So let us consider the first range. So we can say that for x greater than equal to 0 but less than equal to 1, we are given that the potential energy, let us call that a U1, is equal to our E naught, and the total energy is given as twice E naught. Therefore we can say that kinetic energy K1 will be equal to our total energy, that is our E. So we can say our E minus U1, and total energy E is our, let me write here also, this is equal to twice E naught, that is given to us. So we can say E will be equal to twice E naught minus E naught, giving us that our kinetic energy for the first case is equal to our E naught. From here we can easily find out the de-Broglie wavelength, that is our lambda. So we can say that our lambda here it is lambda 1 is equal to h upon the momentum, that is p1, and we can write this as h upon relationship between momentum and kinetic energy we know is about 2m times k1 and its square root. K1 is our E naught. So from here we get our lambda 1 is equal to h upon twice m into k naught, that is our E naught and square root. So this is our lambda 1 for first case. Similarly, we write for our second case. Second case means for value of x is greater than 1. And in this case, our initial energy, let us suppose our U2 is equal to 0. And once again, the total energy, that is our represented as E, is equal to twice E naught. Therefore, kinetic energy, let us suppose we call this as K2, will be equal to total energy E minus U2, and total energy is our E is our twice E naught. U2 is equal to 0. So from here we get our K2 is equal to 2 times E naught. Therefore, de-Broglie wavelength our lambda 2 will be equal to h upon P2, which comes as h upon twice m multiplied by kinetic energy K2. K2 is twice E naught, so we substitute it. We get this as twice m, and we have twice E naught and its whole square root. Now we can easily find out their ratio, lambda 1 upon lambda 2. So we get our lambda 1 upon lambda 2, and lambda 1 is h upon twice m E naught at square root, and this comes h upon twice m, and this is twice E naught square root. And we can just, we get from h and h cancels out, and we are left with as this will be our twice m E naught square root multiplied by square root of 2 and divided by twice m E naught. These two terms cancel out, so we get the ratio is equal to square root of 2. So we get the ratio is square root of 2. Next question. It was also asked in the year 2005, and it states that if the wavelength of the nth line of Lyman series is equal to the de-Broglie wavelength of the electron in initial orbit of a hydrogen-like atom, Z is equal to 11, find the value of n. And here we are given that we are having a nth line Lyman series, and for the Lyman series the transition corresponds to the electron that will be dropping to value of n is equal to 1 from a higher orbit. So we can say that our for Lyman series, electron drops to n equal to 1 from higher orbit. And here we are given as nth line, therefore we can say that it is going to drop from n plus 1 to 1. Therefore, the wavelength if that is represented as given as lambda, so we can write that our 1 upon lambda is equal to r times z square, and here we have 1 upon 1 square minus 1 upon n plus 1 whole square. And for the orbit of this n plus 1 or level of 1 plus 1, n plus 1 rather, we can write the formula for our de-Broglie wavelength. Okay. Value of z is given to us, but anyways we can just sort it out later on also. So we can say that our de-Broglie wavelength for n plus 1, let us call this as lambda, is equal to h upon mass into velocity, and we can use the Bohr quantization. So we can say from Bohr quantization we can write that our MVR is equal to n plus 1 multiplied by h. So therefore we can write that our de-Broglie wavelength, that is our lambda, is equal to h upon, so from here let me write, we can get our MV is equal to n plus 1 multiplied by h divided by r, and we substitute value of MV, we get this as n plus 1, and we have h, and this is multiplied by r. So here h goes with h, and once again and from Bohr quantization we can write this as MVR is equal to n plus 1 multiplied by h quantized, and this also becomes h quantized. Therefore we can write now our lambda, which is equal to h upon mv, giving us h upon n plus 1 h quantized and divided by r. This gives us hr divided by n plus 1, and we have this as h quantized, which will be further written as 2 pi, and we have this as multiplied by r divided by n plus 1. So we got, and here we have to remember that our r is the radius of orbit, which is governed by n plus 1. And the standard formula for our radius of orbit, that is our r, you can say our r is equal to our r naught, and we have this as n plus 1 whole square divided by h, sorry not h but z, and we have our this value of r naught is equal to, that is a Bohr radius is given as 0.0 0.53 into 10 raised to power minus 10 meters. So we can write that our lambda, that is a de-Broglie wavelength, lambda is equal to 2 pi n plus 1 multiplied by r was our r naught, n plus 1 whole square divided by z. And here this square goes by n plus 1, and this comes as our 2 pi r naught n plus 1 divided by z. And we are given that the wavelength of the Lyman series equal to de-Broglie wavelength. So let me make a change here, that our de-Broglie wavelength, let us suppose, is given as lambda dB. So this will be making a comparison easy. So this becomes de-Broglie wavelength, and we are given that both wavelengths are same. Both wavelengths are equal, which basically means that a de-Broglie wavelength is equal to lambda. So we substitute the value and we get lambda dB is our 2 pi r naught n plus 1 divided by z is equal to our lambda, that is 1 upon r z square 1 minus 1 upon n plus 1 whole square. And here this z and square goes away, and on the right side we can just manipulate it, and we get that our we have this as, okay, let's multiply it. So we have our 2 pi r naught n plus 1 multiplied by our rz, and 1 minus 1 plus 1 n plus 1 whole square is equal to 1. And we need to solve this particular combination, this as well as this, because this, and we can combine this one. Okay, so let's write that our n plus 1 into 1 minus 1 upon n plus 1 whole square. So if you multiply inside by n plus 1, this comes as n plus 1 minus 1 upon n plus 1. This gives us n plus 1 is our LCM. So we are left with our n plus 1 whole square minus 1. Therefore, we can write that our, let me combine it. So this comes as 2 pi r naught r multiplied by z, and we are left with this as n plus 1 whole square minus 1, and n plus 1 is equal to 1. So this can be further written as, this is only simple calculation now, we get this as n plus 1 whole square minus 1 divided by n plus 1 is equal to 1 upon 2 pi r naught r times z. And now we can just simply substitute the values. And this will be equal to 1 upon 2 pi. R naught is our 0.53. Zero 0.53 into 10 to the power minus 10, and value of r is 1.1 into 10 to the power 7, and z is given as 11. And from here we get as our n plus 1 whole square minus 1 upon n plus 1 is approximately equal to 24.8. I think this is getting complicated. Hopefully, I think this will be giving us correct answer, hopefully. Okay, so this will be a quadratic equation giving us n plus 1 whole square minus 24.8 into n plus 1 minus 1 is equal to 0. And we can assume this as our x, this will be also our x, so this comes as x square. And we can write x square minus 24.8 times x plus 1, minus 1 is equal to 0. And from here we are going to get two values of x. Let me write them directly. One value of x will be equal to 24.84, and other value of x will be equal to minus 0.045. Obviously we have to neglect this one, so we get our x is equal to 24.84, and that x was equal to our n plus 1. So from here we can say that our n will be equal to 23.84, or we can say approximately equal to 24. So value of n is equal to 24. Next question. It was asked in the year 2006, and it states that the half-life of radioactive substance A is 4 days. The probability that the nucleus will decay in 2 half-life is. So half-life is given as 4, so 2 half-life will be resulting in our 8. So we are given that our half-life is equal to our T1 by 2, that is equal to 4 days, and we can say 2 half-lives will be equal to our 8 days. And we have to find out the probability that the nucleus will decay in this particular time. Okay. So for this we are going to say that we are going to use the reverse part, that the probability that the nucleus has not decayed. Okay. For that we are going to use exponential decay law. So we can say that probability that nucleus has not decayed and let us suppose we call this as P not decayed. that will be equal to our 1 by 2 whole raised power t divided by t half. So we have for two half-lives for two half-lives we can write that our P not decayed will be equal to our 1 by 2 whole raised power 2, which gives us 1 by 4. So therefore we can say that probability of decay probability that it has decayed, let us call this probability as P decayed, which will be equal to 1 minus P not decayed, which is 1 minus 1 by 4, giving us 3 by 4. So option B is correct. Next question. It was also asked in the year 2006, and it states that the graph between 1 upon lambda and stopping potential V of three metals having work function of phi 1, phi 2 and phi 3 in an experiment of photoelectric effect is plotted as shown in the figure. Which of the following statements is or are correct? Here lambda is the wavelength of the incident ray. So basically we have to find out the ratio of the work function, and then we are going to find out the slope, which is of tangent of theta, and we are going to find out the wavelength, or we can say the light which is going to eject electrons from metals 2 and 3. So from first of all the graph is given that we have three metals, metal 1, metal 2 and metal 3, and respectively their work function is also given, that is 0.001, 0.002 as well as 0.004, and this is plotted across the, you can say, the stopping potential V. So from here we can say, or we can write the equation with respect to the inverse of the wavelength, because the graph is given with respect to the inverse. So we can say stopping potential in terms of inverse wavelength. In terms of wavelength, inverse wavelength, we can write that E times our stopping potential Vs is equal to Hc upon lambda minus work function phi. And from here we can say our stopping potential Vs is equal to Hc upon E times lambda minus phi upon E. And this equation is, we can say, is in the standard form of our line equation, and that line equation is our y is equal to mx plus c. So if we make a comparison, we can say our y is equal to a stopping potential Vs, and our x is equal to 1 upon lambda, and our x is 1 upon lambda, m is hc upon E, and we have our c will be equal to minus phi upon E. So we are first of all interested in our slope because we have to find out the tangent of theta. So we can say that the slope of graph Vs versus 1 upon lambda is m is equal to hc upon E. And for if you see that all the graphs are, you can say this slope is dependent upon hc upon E. All these values are constant, and we can also say that our tangent of theta is, I think it is in terms of proportionality, yeah, it is proportional to hc upon E. Now from here we are also going to find out the ratio of their work function. So we are going to use that our y-intercept, that is c is equal to minus phi upon E. So we are given that y-intercept is c is equal to minus phi upon E. And from the figure, from the graph, we can say that from graph we can write the order of y-intercept, order of y-intercept, only magnitude. We can write this as our c1 is our less than c2 is less than our c3. Okay, so c1 c2 is our, so this is our c1 c2 as well as c3, metal 1, metal 2 and metal 3. In we are going to substitute the corresponding for our work function. Therefore we can write our phi 1 upon E is less than phi 2 upon E is less than phi 3 upon E. So from here we can write that our phi 1 is less than our phi 2 is less than our phi 3. And based on the given intercept, the respective intercept are given to us as 0.001, 0.002 as well as 0.004, and we have to remember this is 1 upon lambda. So from here we can write that ratio phi 1 is to phi 2 is to phi 3 will be equal to 1 is to 2 is to 4. So we are having that option C as well as option A is correct. And okay, we need to find out the, check also option D also. So we are having 3 metals, okay. And we can say, we can find out the threshold wavelength. We can write that threshold wavelength for metal 2 Let us suppose that is lambda 2 is equal to hc upon phi 2, and we can write this as hc, and in terms of our phi hc we can just write as phi 2 will be equal to 0.002 times hc, and this will be equal to our 500 nanometer. And similarly for metal 3, we can write this as our lambda 3 is equal to hc upon phi 3, which gives us hc upon 0.004 times hc, and approximately this will be coming as 250 nanometer. So from here we can say that our violet light eject photoelectrons from, it is asked as metal, from metal 2 not from metal 3. I think this was the, yeah, it says that it is going to eject from both, so option D is also incorrect. So only option that our A and C are correct. Option A and C are correct. Next question. It was asked in the year 2007, and it states that the largest wavelength in the ultraviolet region of the hydrogen spectrum is 122 nanometer. The smallest wavelength in the infrared region of the hydrogen spectrum to the nearest integer is. So we are given the largest wavelength, and we have to find out the for the smallest one. So basically this is nothing but our, for infrared region we can say this is our Paschen series. So we have our Paschen series, which is basically our infrared region, and which means that there will be a transition ending at n is equal to 3. So you can say transition ending at n1 is equal to 3. So the lower state will be equal to n1 is equal to 3. So we have to find out the smallest wavelength. Largest wavelength is given to us. So smallest wavelength means highest energy. Smallest wavelength, which basically means highest energy, is transition from n2, which is infinity, to over n1, which we just defined is our 3. Now we can just use the Rydberg formula. And which tells us 1 upon lambda is equal to our r z square 1 upon n1 square minus 1 upon n2 square. And for hydrogen, value of z is equal to 1, and we have to find out the shortest wavelength. So we can just reformulate it. 1 upon lambda minimum will be equal to our r, and n2 is of infinity, so this comes as 1 upon 3 square minus 0, giving us r upon 9. And we can write our lambda minimum will be equal to 9 upon r. R is standard value, that is about 1.1 into 10 to the power 7. Therefore, we can write our lambda minimum is equal to 1.1 into 10 to the power minus 7. This gives us that the minimum is equal to 820 nanometer, and closest integer as per the answer is our 823 nanometer. So option number B is correct. Next question. It was asked in the year 2007, and it states that electron with the de-Broglie wavelength lambda falls on the target in a X-ray tube. The cutoff wavelength of the emitted X-ray is. In this case, we are going to use the electron momentum along with our de-Broglie wavelength. So de-Broglie wavelength is said to be given as lambda. So we can say our lambda is equal to h upon momentum p. So from here we can say our momentum p is equal to h upon lambda. And the kinetic energy of electron, let us suppose that energy is given as E. In terms of momentum, we can write this as p square upon 2m, which gives us our h square upon 2m lambda square. And we have to find out, okay, now this is our kinetic energy, and this energy will be our maximum. We can assume that there is a 100% conversion to the photon. Okay, there is no loss of energy. We can simply assume it because it is nowhere mentioned in the question itself. You can say this kinetic energy is the maximum energy available to generate an X-ray photon upon collision. Or we can say that is cutoff wavelength. So we can write that our energy E is equal to our hc upon lambda naught, and cutoff wavelength is here represented as lambda naught. So let us call this equation number 1 and this is equation number 2. So we can equate both the energies from equation 1 and 2. From equation 1 and 2, we can write our hc upon lambda naught is equal to h upon h square upon 2m lambda square. So here this h goes by square, and we are supposed to find out lambda naught. Therefore we can say our lambda naught is equal to 2mc upon h multiplied by lambda square. So this is our 2mc upon h, 2mc upon h lambda square. Option A is correct. Option A is correct. So this completes a total of 14 questions. From 2004 there were 4 questions, from 2005 6 questions, 2006 2 questions, and from 2007 also 2 questions. So this completes all the 14 questions. Thank you.